Hey there, and welcome. If you've got electricity on your revision schedule for your exams, you are in exactly the right place. We're about to do a super quick, super powerful run-through to get you totally ready. So let's jump right in. All right, so the goal here is simple, to get you feeling prepped and super confident. We're going to cover all the essentials, touch on some of the trickier bits, and look at the practical stuff you absolutely need to know. By the end of this, you'll be ready to smash those exam questions. First things first, let's do a really quick recap of the absolute basics. You know, these are the big three, the foundation for literally everything else we're going to talk about. If you get a solid grip on these, you're building on a fantastic foundation. All right, here they are, our big three. We've got current, potential difference, and resistance. And you'll see their symbols, I, V, and R, all over the place. So let's quickly break down what each one of these actually is. Okay, first up is current, or I. The easiest way to think about current is that it's all about the flow. It's a measure of how much electric charge is moving past a point in a certain amount of time. We measure this flow in something called amperes, or you'll usually just hear it called amps. But for that current to actually flow, it needs a bit of a push, right? Well, that's where potential difference comes in. You probably know it by its more common name, voltage. It's the oomph, the driving force that makes the current move. And, no surprises here, we measure that push in volts. And rounding out our big three is resistance. In any circuit, there are things that try to slow that current down. Resistance is basically electrical friction. The more resistance you have, the tougher it is for that current to get through. We measure this in ohms. Great, so we've got the what down. Now let's move on to the how. How do we actually measure this stuff? In this section, we're going to look at the tools for the job and the one single super important rule that connects all three of our core concepts. This is key stuff. So picture this. You're in the lab, you've built a circuit, and you need to know what the current or the voltage is. What tools do you grab? And maybe more importantly, how do you actually connect them? Because getting this wrong is a really common mistake. Okay, this slide breaks it down perfectly. To measure the current, you need an ammeter, and you have to connect it in series. That means you literally break the circuit and stick the ammeter in so it becomes part of the main loop. But for voltage, you use a voltmeter, and that gets connected in parallel. It goes across a component, not in line with it. Seriously, if you remember one thing here, make it this: ammeter in series, voltmeter in parallel. So we've got our big three: voltage, current, and resistance. They can't just be floating around on their own, right? Is there like one rule to rule them all? A single simple formula that ties them all together? Oh, you bet there is. And it's probably the most important one you're going to learn. And here it is, the one, the only, Ohm's law. V equals I times R, or voltage equals current times resistance. This little equation is basically your golden ticket for solving a ton of electricity problems. If you know any two of those values, you can always figure out the third one. It's that powerful. Let's actually put this into practice, shall we? Say a question asks you to find the current. Step 1, you might need to rearrange the formula. So I equals V divided by R. Step 2, you just plug in the numbers you're given. Let's say a voltage of 12 volts and a resistance of 6 ohms. Step 3, do the math. 12 divided by 6 is 2. The current is 2 amps. See? Simple as that. Okay, so we've got the core concepts, and we've got the main formula. Now let's see what happens when we use them to build actual circuits. There are really two main ways to wire things up: in series, where there's just one path, and in parallel, where there are multiple branches. Let's see how they're different. This table is an absolute lifesaver for revision, seriously. Let's walk through it. In a series circuit, there's only one path, so the current has nowhere else to go. It's the same everywhere. But the voltage gets shared or split between all the different components. Now look at parallel. It's the complete opposite. The current splits to go down the different paths, but the voltage is the same across every single branch. And now for the really interesting bit: resistance. In series, it just adds up, makes sense. But in parallel, and this is a key idea, the more resistors you add, the lower the total resistance gets. Why? Well, think of it like opening more checkout lanes at a supermarket. You're giving the current more paths to flow through, so the overall bottleneck, the total opposition, actually goes down. Okay, enough theory for a second. Let's get to the really cool stuff. I mean, why do we even care so much about electricity? Well, it's because we can use it to create some incredibly powerful and useful effects. Let's look at the three main ones that have pretty much changed the world. So, what are these amazing effects? Well, we're going to look at the chemical effect, the heating effect, and the magnetic effect. And trust me, each one lets us do some incredible things, from making everyday gadgets to performing life-saving medical procedures. So first, let's talk about the chemical effect. Basically, if you pass an electric current through certain liquids, you can force a chemical reaction to happen. This is the secret behind electroplating. That's how you coat a cheap metal with a thin layer of something fancy like silver or gold. It's also used to extract pure metals from raw ore. Next up is the one you absolutely use every single day, the heating effect. Whenever a current flows through something with high resistance, it generates heat, a lot of heat. Think about the glowing wires in your toaster, your hairdryer, or even the massive autoclaves in hospitals that use superheated steam to sterilize equipment. And last, but definitely not least, is the incredible magnetic effect. When you pass a current through a coil of wire, it magically becomes a powerful magnet, an electromagnet. You can turn it on and off. This is the mind-blowing tech behind things like MRI scanners that let doctors see inside your body, and even super precise robotic tools used in surgery. Okay, so we've established that electricity is amazing and powerful, but with great power comes the need to be safe and smart, right? This last section is all about using electricity wisely, which is not just useful for your exams, it's useful for your whole life. So let's bring this right back home. Literally, electricity is all around us. But what are the actual real-world risks? Knowing what the common dangers are is the first, most important step in keeping yourself safe. Yeah, here are 4 of the big ones you really need to watch out for. Overloading sockets, plugging too many high-powered things into one extension cord, can cause overheating and even fires. Frayed or damaged wires can expose the live electrical part, which is a huge shock hazard. Using anything electric in wet or damp conditions, like the bathroom, is a big no-no because water conducts electricity. And, of course, never ever tamper with sockets. The good news is our homes are packed with safety gear to protect us. You've got fuses, which have a tiny wire inside that's designed to melt and break the circuit if the current gets dangerously high. It's a one-time use device. Then you have circuit breakers. They do the same job, but instead of melting, a switch just trips to cut the power. The big advantage? You can just flip it back on again once it's safe. No replacement needed. Have you ever looked at an electricity bill and seen kWh and wondered what on earth that means? It stands for kilowatt hour, and it's simply the unit we use to measure how much electrical energy you've used. It's actually pretty simple. It's the amount of energy a 1 kilowatt device would use if you left it running for 1 full hour. So what can you actually do to use less of those kilowatt hours and maybe save some money? Well, it's easier than you think. When you can, choose energy-efficient appliances. Switch things off at the wall. That standby light is still using power. Be smart about big energy users like water heaters and air conditioners. And little things, like using a vacuum flask to keep water hot instead of reboiling the kettle, all add up. And that's a wrap, a full revision of the essentials of electricity. We've hit the basics, the main rule, the different circuits, and the practical side of safety and saving energy. So the final question isn't for me, it's for you. Now that you understand the rules, how are you going to use this incredible power wisely and safely? You've got this. Now go and ace those exams.